Hi, good morning. It's 6:37. I'm Charlie Bouman, and we're here today to learn about sampling and filters and focal plane arrays. So let's see. Let's pick up where we left off. So this is a focal plane array. So each of these cells, this could be modeling mathematically either a CCD or a CMOS device. And I think I talked a little bit about that. CMOS devices are becoming more popular, but CCDs have been the traditional method for acquiring digital images. So basically, each of these cells integrates all the photons that come in over that square. And in an ideal situation, the squares don't overlap, but they fill up the cell completely. In practice, there's usually some space in between that the photons that are filled with like electronics, so the photons can't be captured effectively there. But if the electronics is small, then you try to have higher efficiency. You don't want to waste any photons so that all the photons are collected. Hold on for just a second. I have to take off my sweater. So that's sort of the situation. So mathematically, you can each of these cells is t by t. So you can model that as the integral. So let's say that the position of the cell, let's say the first cell is at 0, 0. So then, so the ijth cell, if you take that as I, so then it's going to be I times t is going to be the position here, and j would be like, this would be j times t. So you're going to have a function h of xy. It's just, that's the aperture function. So it's going to be h of xy, and for the ijth center, it's going to be h of x minus ti, y minus, jt, because this is the shift in x, and that's the shift in y, right? And then you take the incoming photon, so let's say the f of xy represents the field of incoming photons, and what you'll actually measure from the ijth sensor is this integral. Of course, over time, too, because there's some time aperture. So this might be the rate of photons. And then this will be the output you get. So this might be what you'd call, I want to make my notes consistent. So what am I calling that? I guess I'm calling it SMN. Sij. So that's the measurement from the ijth sensor, that integral. Okay. Now, if I, so you'd say, well, this looks a lot like a convolution. If I replace this by, I replace this variable here by xi. I'm running out of variables, so I'll use xi there, and this will be eta. Okay. Then this looks like, if I define g of xi eta to be equal to the integral over f of xy, h of x minus xi, I keep making betas, xi y minus eta dx dy, okay, then this almost looks like convolution. It would be convolution if I just had the negative here. You know, by the convolution is commutative. So this is the same as the integral of h of x. Oh, hold on for a second. Oh no, it's okay the way it is. That's right. So if I took the negative of this, that's the integral. Oh, hold on. This is getting too sloppy. Let me rewrite that. I'm sorry. So I have that g of xi eta is equal to the integral of f of xy. I'm just recopying my equation so it's not so sloppy. X minus xi, y minus eta, dx dy, right? So that's not quite convolution, but I can make it into convolution if I just rewrite it this way. Right? Now it looks like convolution. It looks like convolution between f of xy and h of minus x minus y. Now h is often a symmetric function spatially, so you don't notice the difference between convolution with the space reverse and the original function. Okay, so, this is convolution. Right? So basically we have two equations. G of zeta eta is equal to f of xy convolved with the time reverse of x and y, and then s of nm is equal to g of nt mt. So this is sampling. So this is filter and sample. Okay? And the filter here, h of, oops, there's minus sign there too. H of xy, it's a rectangular filter with t, okay? So it's rect of x over t, y over t, and I don't know if I normalize this in the notes. Yeah, okay, so I normalize it t squared, so it integrates to 1. So the effect of a imaging sensor like this is really you take the image f of xy, you pass it through a filter h of minus x minus y, then you sample. Right? And so if you go to reconstruct, effectively what's happened is that you've filtered the image. So what that really means is that you'll get this causes some blurring. So in the frequency domain, you'll get that this is S of Mn. So this has a discrete time Fourier transform of S of e to the j mu e to the j nu, and this has a continuous time Fourier transform of f of uv, right? So S of e to the j mu e to the j nu, we know that that's equal to 1 over t of the signal that was sampled. So this is g of xy. Actually, did I put a tilde on that? I don't even remember why I put a tilde on that. Oh, because my original signal was I'll use I'll use a little different notation here. So this is g of xy. So that's going to be equal to the sum over k and the sum over L of g of, this will be mu minus 2 pi k over 2 pi t, and this is nu minus 2 pi L over 2 pi t, right? Right. But g here is really g of uv is really going to be h of uv times f of uv, where this is the frequency response of the filter, and the filter, so this would be the dTft of the rect, so that turns out to be the Sinc, and it becomes, let's see, so here, okay, so the Sinc here, oh, let me see, okay, so this is a rec of x over t, so let's see, oh, so there's kind of an interesting thing happens here. So this is the Fourier transform of rec is a Sinc. So this is Sinc of u times t, and this is v times t, right? But when I plug this into here, so this equation becomes s of e to the j mu, e to the j nu is equal to 1 over t times the sum over k and L. This becomes h of mu minus 2 pi k over 2 pi t, comma, nu minus 2 pi L over 2 pi t times g of mu minus 2 pi k over 2 pi t, comma, oh, I'm running out of space here, so this is nu minus 2 pi L over 2 pi t. Okay, so that's, oh, I'm sorry, this isn't a G, this is an F. It completely changes things. Okay, so what I'm doing here is, this is the formula which relates, the discrete time Fourier transform of the sampled signal to the continuous time Fourier transform of this virtual signal that would have resulted by filtering the original image with this square pulse associated with the aperture of the imaging sensor. Okay, so this is just the sampling formula, right? But really, G is equal to H times F. So I have to plug this into here, and that's what I'm doing here. Okay, now H here has the form of U times T and V times T. So this T cancels with that T, right? Because this Sinc here is what H is. See, that Sinc function is H, so that H plugs into here. So this H here becomes Sinc of mu minus 2 pi k over 2 pi, and the T's cancel. And this becomes mu minus 2 pi L over 2 pi. So the final formula becomes that the sampled signal S of e to the j mu, e to the j mu, is equal to, oh, this is a t squared. That should be a t squared, yeah. Actually, that's a t squared there, and that's a t squared there. It's squared because it's in 2 dimensions. So this becomes 1 over t squared, sum over k and L. I'll put the other sum in there so it doesn't confuse you. And this becomes Sinc of mu minus 2 pi k over 2 pi nu over 2 pi L over 2 pi. And this is f of mu minus 2 pi k over 2 pi t. And this is mu minus 2 pi L over 2 pi t. Now, if there's no aliasing, okay, so if no aliasing, then the formula simplifies for mu less than pi and for nu less than pi. And for that case, I can write the formula down, and I get that S of e to the j mu e to the j nu is equal to 1 over t squared sinc of mu over 2 pi nu over 2 pi times f of mu over 2 pi t nu over 2 pi t. I know there were a lot of steps there, but you know what? There really are simple steps. You just have to go through each step one at a time and verify that you agree that it's correct. And notice I don't allow for the possibility of disagreement. Okay, well, I guess it's possible. Okay. So that's all these equations actually in the notes. So in the end, so hold on for a second. So in the end, so I get that. And then now what happens is that we've done reconstruction, right? Where's reconstruction? 2D sampling. What happened to reconstruction? Okay, so the formula for reconstruction is that so now, okay, reconstruction. What is reconstruction? Well, if you have a display, okay, so that's your display, okay, so your TV set or whatever, okay, and over here you have a computer, okay, and that's the wire attaching them, okay, and you download an image, okay. Now the image is going to be like S of n m, okay, and for each n and m is a float, right? Or a double or an int or an unsigned character, usually an unsigned character for each color. And so this is acting like a D to A converter. You can think of this as one big D to A, right? That's producing a light field from your digital specification of the input. So the actual light field, f of xy, then, is going to be equal to, maybe I'll put a tilde on this because this is the reproduced quantity, is going to be the sum over n and the sum over m of S of mn. Oh, I got my m's and my n's mixed up here. Right? That should be an m and that should be an n. Okay. Of p of x minus mt y minus nt. Now we're assuming here that the display is displaying the image the same size as it was obtained. Of course, they don't have to be the same, okay? But for reasons of simplicity, we'll assume that they are mathematically, okay? But what happens is that this is like, the output of this is continuous in space, and the input's discrete. So this is the like the PSF of display. They used to call this the the pixel profile or something like that. I don't know. They used to talk about this more with analog displays like CRTs. For a display that's digital, usually that number is basically it's specified, right? And it's going to be basically the same thing. It's going to be also a rectangular function. Hold on, I think I have this. Okay, so, but whatever it is, and then if you have P of xy, its continuous space Fourier transform is f of uv, right? So if you put that together, so in the frequency domain, it's going to turn out that f tilde of uv is going to be equal to s of I said s and I wrote e. S of e to the j mu e to the j nu, okay, times p of times this is times t. Oh gosh, that's times t times p of oh gosh, this is supposed to be a p of uv. So this is a relationship. This is the Reconstruction Formula. That if you have, let me back up just slightly and just point this out. That if you have S of n, let's say in 1D, S of n, okay, and it goes into something which reconstruction, and the output here is the sum over n of p of t minus nt times s of n. So this generates a pulse train of t. This generates a pulse train. So what happens is here you have a discrete time signal. So what's the value halfway between two samples in this discrete time signal? So this would be like S of 0, and this is S of 1, this is S of 2. What's the value halfway between? Is it 0? No. It's not 0, right? Is it infinity? No. It's not. Okay, it's not defined, okay? So it's not defined, okay? But then when over here what happens is, and this is 0, this is 1, this is 2, right? And then over here you replace each of these with like a little blob. And the blobs can overlap, as a matter of fact. Oh, I'm really doing a lousy job of drawing this, okay? Especially because there's no relationship between these values. And these are supposed to map together, okay? And I've got it all messed up. Okay, but, okay, I'm sorry. Okay, so I'm not Picasso.
Yeah. Yeah, that's a good point. Where are you?
So this is t. See, this is n. This is discrete time. That's continuous time. And these values modulate the size of those pulses, right? Right? So then when you're all finished, you get, I'll use the red one here. I'll really get fancy. Of course, it goes like something like that, right? Okay? So this thing here, f tilde of u, okay, or of f, I'm sorry, frequency, and this one here would be s of e to the j omega, right? This will be equal to s of e to the j omega t. Oh, and these values are like 0, t, 2t, 3t, right? This is omega t times p of f. So this is the Reconstruction Formula. All right? And the generalization to 2D is what we just did. So what this always tells you is in the frequency domain, when you go to do reconstruction, what will end up happening is that you'll have this thing always has to be periodic with period 2 pi. So when you multiply by t, it becomes periodic with period fs, where fs is the sampling frequency. So what will end up happening is you'll have something like this. So this is fs over 2, and this is fs, and this is fs over 2 times 3, okay? So you'll get like this. All right, like that. And then what will happen is this P of F, well, now ideally it might be a sharp cutoff, okay? But it doesn't have to be. If in the case of the display, okay, in the old CRT tubes, these little pulses could overlap. But in the LCD displays, they can't really, because each LCD element is physically separated on the surface of the display. It's a separate. I mean, if you look at the surface of an LCD display with a magnifying glass, they're little square rectangles, okay? Little squares that overlap, okay? Or they can overlap, okay? So what'll happen if the pulse has finite support, then certainly you can't get any frequency response you want. And in fact, there's a theorem which says that if you have something which is bounded in frequency, it's unbounded in okay, let me say it the other way. If it's bounded in time, it's unbounded in frequency. If it's bounded in frequency, it's unbounded in time. So since this is if it's bounded in time or space, it's got to be unbounded in frequency. So you can't get a perfect cutoff. What you'd like to do is just pick off this one term, and then you would get just the unaliased thing. But that's not quite what will happen. You'll get something like this. Okay, and then you'll get some aliasing that'll remain. But hopefully you sort of attenuate a lot of that, okay? All right? So this is reconstruction. Are there any questions about this? Yeah.
Deterministic, right? I mean, we know what is
PF. Yeah, or PT you said.
PT.
Yeah. So the assumption is that the system has a reproducible pulse that it produces, and it only modulates the amplitude of the pulse, but not its shape or any other characteristic. Right? That's an approximation, as are all models, right? But on the surface of a display, that's for LCD display, that's pretty accurate, because I mean, just like I said, for the LCD display, if you take a magnifying glass, it's like this, right? Now I'm simplifying. I'm not going to worry about color. With color, they do what's called color mosaicing, okay? But basically, each of these little squares, you modulate the light intensity of the square. So each pulse is a little square. So it's the same kind of thing. P of xy in this case is actually rect of x over t, y over t. Okay? Okay. Okay. So coming back to this is what I'm saying here, that's where this formula here came from. This is just a two-dimensional generalization of the previous formula. Right? So you took the discrete time Fourier transform. The discrete time Fourier transform has units along the axis of radians, okay? So you have to convert the hertz. The way you convert the hertz is by multiplying by t. Now what happens is that this becomes units of hertz, because if a mu is in hertz, okay, then you multiply by t. Hertz are units of 1 over time. You multiply by time, and it becomes unitless. So when anything you exponentiate really needs to be unitless. Okay. So then this is periodic with period fs, where fs is the sampling frequency in both axes, mu and u and v, right? And then this is sort of the filter that is in red in this diagram here. Okay? Does that make sense? So now, plugging that all together, I get that F tilde. And okay, now what I do is use the previous form. If I take all the terms, I get this. Okay, that include the Earlyson terms. And the Earlyson terms will remain. I mean, you can't remove them completely. But if you only look at the low frequency term, the sort of baseband term, that's this, okay? And if I plug this into this, you see, because that's S of e to the j mu, and S of e to the j mu, S of e to the j mu, e to the j nu, right? That's this S right here. So I can take this expression and plug it into here. Then I get the full expression for the output image as a function of the input image. And it's like this. It becomes sinc of u over 2 pi t, v over 2 pi t, and this is p of u v, and this whole thing is over t squared, and this whole thing will be f of these t's go away because this t here, hold on for a second. Oh no, the t's go up here. S of e to okay, the t's go here. I'm sorry, and this mu here, this t cancels with that t. So you get, this becomes f of oh gosh, I screwed something else up. I'm sorry. I got radians and frequency messed up. Okay. This is a U and this is a V. Okay, and this is there's got to be a 2 pi in here. I'm sorry. This is why it's better to do this stuff in notes. And in fact, if you notice, my equation doesn't even make any sense here, okay? Because I have the F. Don't ever do this on an exam, okay? You'll lose full credit. I just illustrated to you precisely what you should never, ever, ever do, okay? I have F. This equation makes no sense at all, okay? Because here I have F, and here I have omega, right? It's nonsense. Oh, but my heart was in the right place, okay? Because this omega is supposed to be a 2 pi f, okay? So I have to, actually, that's one reason I always use f in continuous time frequency and omega in discrete time frequency, because it helps catch errors in your equations. Okay, so when all that cancels out, this 2 pi goes away also. And then this becomes, I shouldn't derive these like this, huh? This becomes U and V. See, I know it has to come out that this signal has to have the same coordinates UV as on the left and right hand side. Otherwise, there would be some kind of scaling, and there shouldn't be. Okay, so this expression here is like H of UV. It's a filter. So, okay, so what happened is I sampled the image, I stored it, and I displayed it. And the overall effect is not to reproduce exactly the same image. It's to produce an image, even if you ignore the aliasing terms, it's to produce an image which has been filtered by this. It's the convolution of the point spread function of the display and the sampling function of the acquisition, right? Of the CCD. So H here H of UV is equal to Sinc of UT times VT times P of UV over T squared, right? And if P of UV is the same thing as Sinc, very often, like at a flat panel display, P of UV will equal Sinc of UT VT. Also, because it's also a square pulse with the same size as the pulse that was used for the imaging sensor. Because P of xy is equal to rect of x over t, y over t. No, there's a scaling term here. So the scaling term is, so this becomes larger with t becoming larger. So you have to divide by t squared, right? Okay. If not, then the other way to do it is to put a t squared here. So if that's correct, then h of uv is equal to Sinc of ut vt squared times P of uv. And another way of writing that is that this is Sinc of u over fs, v over fs squared times P of uv.
Do you mean Sinc of ut vt squared without the p on the side there? Because we just defined
yeah.
p as...
I'm sorry. Thank you.
Yep.
I'm glad somebody's paying attention. Other than, certainly I'm not, I guess. Okay. Oh, well. Okay. Yeah, good. Okay, now, so now we can plot a Sinc function. Okay, so this is Fs. This is Fs over 2. This is minus Fs over 2. This is minus Fs, okay? The Sinc function then has its nulls at integers. So it's going to have a null here. So this is Sinc of u over fs, v over fs, but we're squaring it. So it looks like this. Wait, hold on. I got this messed up. Okay. So the first null is at 1. This is 2fs minus 2fs. So this is fs. This is minus fs. This is 2fs. This is 2fs. This is 3fs. All right. This is Sinc of u over fs, v over fs squared. Okay. Now, the only frequencies you're supposed to care about are up to fs over 2. So these are the frequencies you care about. Ideally, what you'd want is a filter like this. So, but what you're getting is a filter like that. Okay? So this is roll-off. That tends to, so you're attenuating the high frequencies a little bit. Remember, anything out of here, anything behind here these are aliased frequencies. All right? So these frequencies were supposed to be removed in the first place. But here in the band of the frequencies you're supposed to be preserving, ideally you'd want this filter to be flat. But instead it's giving you a roll-off. And the roll-off is the convolution of the response of the CCD with the response of the display. And if you sort of use a simple theoretical model, that's going to be Sinc squared, because one Sinc is because of the square. Remember, the Sinc is coming from the Fourier transform of the rect, and the rect is coming from the fact that the little pulse in the CCD is square, right? And the other rect is coming from the fact that in the display, this is the LCD display, each of these little guys is square, okay? So the convolution of those two squares together produces a Sinc squared roll-off. So what this really just means is that, and it's kind of a theoretical treatment, I think there's a lot of other practical issues that are probably just as dominant, but at least it gives you a sort of a theoretical basis to see that even if you have a perfect camera and a perfect display, perfect, quote unquote, okay, here I'll say, perfect, okay? Okay, I don't know what perfect means, okay? But whatever perfect means, even if you have a perfect camera and display, the image will still be too soft. Soft means it's the terminology that's used to say if the high frequencies have been attenuated in the image. It doesn't look typically as sharp, okay? So, and you've done the you did the lab, right, on filtering, and you implemented an unsharp mask, right? So, that's like, an unsharp mask is like a not unhappy person. Okay, so an unsharp mask is something that removes the unsharp components. Okay, so if you remove the unsharp components, you must be making it sharp. Okay, so by removing the unsharp components, by adding sharpness, okay, which is the simpler way to say it. It's not my fault. I didn't name it, okay? But you implemented it. You can sharpen the image and compensate for this attenuation, okay? And ideally, you'd want it to be the inverse of this. But I wouldn't get too carried away with it because this is all a pretty approximate model. The upshot of it all is just that the image is softer after acquisition and display than you would like it to be, even to accurately render the original image. So do a little bit of sharpening, okay? Any questions about that? Okay. Yeah.
So, this thing gets sent to a IR filter, and
yeah. Well, it wasn't IRR. It wasn't an IIR filter. It was actually an FIR filter in your lab, and that's actually how unsharp masks are typically implemented. Okay. Do you know what I'm saying?
yeah,
Right. And the way the unsharp mask, by the way, worked, and it's a very this is the advantage of doing labs first, so that way you actually understand it before I talk about it in a lecture. But okay, what you do is you compute sort of the average of the image locally. So this is a local average. So that's sort of the blurred component of the image, right? And then you take F and M, and you subtract that from it a little bit, right? And, oh no, hold on for a second. So let me see. You take this minus this, and then that's the sharp component, okay? You take, okay, so this is, yeah, so this is smooth. Okay, this is sharp part, right? And then you take this, you add a little bit of this back to the original image. And this is sharpened. That's the sharpened image, okay? And this is just the sharp part. This is just the high frequency part, right? Because you've in the frequency domain, you had something that kind of looked like this. And then when you subtracted that component from the original image, you got something that looked like this. Okay? This is the sharp part, and then you add a little bit of the sharp part to the original image, and you get something that looks like this. I'm not drawing it very well, but so you get and this is pi and minus pi. This is pi and minus pi. So you get and the amplitude of this is lambda. So you sharpen the image to try to recover some of this attenuation here. All right. Okay. And this just explains that. Okay, and then let me just finish up on this one thing, and then we'll be on to the next topic. And the next topic is filters. Okay, raster ordering, I think that we already know a lot about this, but this just formalizes the idea that one thing that happens is that, people often call a 2D array, they call it a matrix. I object to that terminology. So this is not a matrix in always, at least not always. If it's an image, so this is an image. And the reason is this. A matrix is an operator, right? So you take AX equals Y. Okay, this is a vector. Vectors are data, okay? This is an operator. And this is data. Okay? This is images are not usually operators. I mean, you could take them and use them as operators, but it'd be pretty weird. It'd be like generating data in C and running it as a program. You can do that too, right? Because C is perfectly happy to execute random pieces of data as instructions. Of course, you'll very rapidly get a segmentation fault or a bus error, okay, because it'll be crazy nonsense, okay? But it's the same thing here. Data is, an image is not an operator usually. It's usually data, okay? So the natural format for an image from a mathematical point of view, it's a 2D array of data, but it's not a matrix. When we represent it, we really want to make it into a vector, which confuses people a lot. Okay, so there's lots of ways you can make it a vector. You just have to reorder the points. But a typical way of doing it is to use raster ordering. Okay, see left to right, top to bottom. Why not? Okay, as good as anything. So that's fine, and you can go in either direction then. Also, the other thing is that, okay, so in the computer, nothing is really a 2D array either, because the computer only has one-dimensional memory access. I mean, you could make a computer that had a bus architecture that used a two-dimensional array, but nobody does, okay? And I don't think it's going to be happening anytime soon. So you have to use one-dimensional arrays of data. And the caching is all done one-dimensionally. So you have to map this 1D to 2D. So this is the mapping from 1D to 2D, and this is the mapping from 2D to 1D. And you can just look at that. You can either do that mapping explicitly or implicitly. And let's see. Let me just touch on filters. And now, the nice thing is you've done the lab on filters, so you probably more or less understand it. There's two kinds of filters, FIR and IIR. FIR is finite impulse response, and it means that you literally implement the convolution. The advantage of FIR is it's simple and it's easy to specify. The difficulty with FIR is that it tends to require a lot of computation, because let's say you have an n by n window for computing the output for each pixel. Then the amount of computation per pixel is n squared, right? Per pixel times the number of pixels. Let's make this, yeah. So this is n squared multiplies per pixel. So let's say you have 1,000,000 pixels and you have a 10 by 10 window. If n equals 10, that implies that n squared is 100, right? So that's 100 times 1,000,000 is 100 billion multiplies just to do a filtering of one image, which is a lot. Okay, so we'll talk about IR filters next time. We'll talk about edge detection also. Good. Well, thanks a lot.